Hello everyone, this is your channel Physics with Shomita and I am Shomita Gupta Roy, and today we are going to study energy band in solids. Now, in an isolated atom, the energy of an electron is same as that of the orbit it is revolving in. Okay, in an isolated atom, the energy of the electron is same as that of the orbit it is revolving in. Like the energy of an electron in the nth orbit of an atom is given by minus 13.6 z square by n square. We have known it from Bohr's atomic model. Okay, now for hydrogen atom, putting z equal to 1, we get for the first orbit of hydrogen atom or the ground state or the K shell, the energy of the electron is minus 13.6 electron volt. For the second orbit of hydrogen atom or the first excited state or the L shell, the energy of the electron is minus 3.4 electron volt. In the third orbit of hydrogen atom, it is minus 1.51 electron volt. In the fourth orbit of hydrogen atom or the N shell or the third excited state, it is minus 0.85 electron volt, and so on. Okay, but see, in hydrogen, the energy of an electron in an orbit depends on the principal quantum number n. Energy of an electron, it depends upon the principal quantum number minus 13.6, z is equal to 1 by n square. Okay, so energy of an electron in hydrogen depends on the principal quantum number. In an orbit, the energy of an electron in an orbit depends upon the principal quantum number, n. Okay, so if the third shell, like the M shell, it is consists of 3s, 3p, 3d subshells, all have the same energy. Okay, but in many electron atom, in a many electron system, in a system consisting of an atom consisting of many electrons, there are electron-electron repulsions causing different subshells to be at different energies. Okay, like for example 2s, the 2s subshell will have in a many electron atom, 2s subshell will have different energy from 2p subshell, because 2s subshell is closer to the nucleus. So if a shell is closer to the nucleus, means the electron in that shell is closer to the nucleus. So electron is undergoing an electrostatic force of attraction. So whenever forces are attractive forces, potential energy decreases. So the energy decreases. Okay, so 2s subshell, since it is closer to the nucleus, it will have lesser energy than 2p subshell. Okay, though they are in the second orbit, n equal to 2. So that is different in many electron atoms. Okay, like we take the example of sodium. Okay, and we draw the energy levels of sodium. For sodium, the atomic number Z equal to 11 and the ground state electronic configuration is 1s2, 2s2, 2p6 and 3s1. Okay, so there are 2 electrons in the 1s shell, 2 electrons in the 2s shell, 6 electrons in the 2p shell and 1 electron in 3s subset shell. Okay, so here you see, if I take an isolated sodium atom and I am talking about the electron in the 3s orbital. Okay, I am talking about the electron in the 3s orbital. If I take an isolated sodium atom, the energy of the electron in the 3s orbital, whatever may be the energy, we are not counting that, but the energy of an electron in the 3s orbital, in the outermost orbital of sodium atom, of an isolated sodium atom, will be the same as of this isolated sodium atom. Okay, the energy of the electron in the 3s orbital of an isolated sodium atom, for all isolated sodium atoms, the energy of the electron in the 3s orbital will be the same, isn't it? But if 2 sodium atoms are brought closer to each other, then there are interactions between the electrons and the electrons and the neighboring nuclei. So if two sodium atoms are brought closer to each other, almost forming a molecule, then there will be interactions between the electrons and between the electrons and the nuclei. Okay, whereby the energies of the electron in the 3s orbital will be different from that of the electron in the isolated atom. Okay, the energy of the electron in the 3s orbital in a when the two atoms are closer to each other, almost forming a molecule, like when two atoms comes closer to a distance of 2 angstrom to 3 angstrom, okay, almost forming a molecule, then there are interactions between the between the electrons and the neighboring nuclei, whereby the energy of the electron in the 3s orbital changes. 3s atomic orbital, the energy of the electron in the 3s atomic orbital changes. It is different from the energy of the electron in the 3s atomic orbital of this isolated atom. So this now Pauli's exclusion principle, what does it say? What does Pauli's exclusion principle say? Now Pauli's exclusion principle, it says that no two electrons in an interacting system can have the same energy or the same quantum state. I write it down. No two electrons in an interacting system can have the same energy or the same quantum state. So the atomic orbital of 3s atomic orbital, the energy of this 3s atomic orbital will be different from the energy of 3s atomic orbital. And these two energies of 3s atomic orbital will be different from the energy of the 3s atomic orbital of the isolated atom. Okay. So these two atomic orbitals, the atoms are close together, almost forming a sodium molecule, but these two energies of these two atomic orbitals, they are 3s atomic orbitals, the energies of these two atomic orbitals will be different. Okay, now there is overlapping because of Pauli's exclusion principle. The 1s atomic orbital cannot accommodate, or the 3s, we are talking of 3s atomic orbital, it cannot accommodate one more electron. Okay, in the same energy level, it cannot accommodate one more electron. So the atomic orbital or the 3s energy level will split into two energy levels. Or you may say there is overlapping of atomic orbitals to form a molecular orbital. Overlapping of atomic orbitals to form a molecular orbital. There are two 3s energy levels. Okay, each energy level containing one electron, which means that energy of this electron is different from energy of this electron. These two electrons are not the same. And the energies of this two electrons is again different from the energy of this electron, all being at 3s level, energy level. Okay, so there is splitting of this energy level. You understood the meaning of splitting of the energy level. The energy of this electron is different from energy of this electron, both being at 3s energy level. There is splitting of this 3s energy level into two energy levels when two atoms are close together to form a molecule. So these two energy levels, they are actually forming a molecular orbital. They are actually called anti-bonding orbitals, bonding orbitals. Bonding orbitals, actually molecular orbital are of three types. Bonding orbital, the atomic orbitals overlap to give molecular orbital. Molecular orbital are of three types: bonding orbital, anti-bonding orbital, and non-bonding orbital. And non-bonding orbital. What are bonding orbital? Bonding orbital means This orbital, this energy level, say this energy level I'm talking about 3s. This is the 3s molecular orbital. Okay, so molecular orbital consisting of two energy levels now, two atoms closer together, almost forming a molecule. So two energy levels, split it into two energy levels. So I'm talking about this energy level, they form a molecular bonding orbital. Means the energy of this molecular orbital is less than the energy of the atomic orbitals forming them. It is the overlapping of two atomic orbitals to form a molecular orbital. So this molecular orbital has energy less than the constituent atomic orbitals forming them. Okay, thereby promoting the chemical bond between the molecules and helping in the bonding of molecules. Now suppose the upper energy level molecular orbital is called anti-bonding orbital. Anti-bonding orbital means the orbital has higher energy than the energy of the constituent atomic orbitals forming them. Constituent atomic orbitals. These atomic orbitals are forming the molecular orbital, right? These two atoms have come closer together. So this anti-bonding orbital means it has energy higher than the constituent atomic orbitals forming them, thereby opposing the bonding of molecules. And non-bonding orbital means it has the same energy as that of the atomic orbitals forming them and has no effect on bonding of molecules. Okay, so non-bonding orbitals, it doesn't actually exist because molecular orbital will never have an energy same as that of the atomic orbitals. Okay, so now if three atoms come close together, then how many energy levels will there be? If three atoms come close together, okay, then how many energy levels will there be in 3s? I'm talking about 3s atomic orbitals. 3s atomic orbital. So 3s atomic orbital, or 3s molecular orbital, because the atomic orbitals will overlap to give molecular orbital, okay, will consist of three energy levels. The 3s molecular orbital will consist of three energy levels. So in one mole of sodium, consisting of n atoms means 6 into 10 to the power 23 atoms. How many energy levels will be there? The 3s molecular orbital will have n energy levels. N energy levels means how many? 10 to the power 23. That is nearly 10 to the power 23 energy levels. Okay, so it is something like this. Now I'm not saying that the electrons which are there in the interior, like in the 1s, 2s, 2p in this shells, in the second shell, in the third outermost shell, it is in the 3s orbital, it is actually breaking up into 10 to the power 23 energy levels, doesn't mean the inner energy levels does not get splitted. They also get splitted up, but they get splitted up. Actually there are less interactions of the electrons which are inside the okay, there are lesser splitting up of the energy levels of those energy levels, okay, than the electrons which are in the outer orbitals. The inner orbitals, electrons in the inner orbitals, those orbitals have lesser splitting up of the energy levels, because these electrons in the inner orbitals will have less encounter with the neighboring atoms, will have less encounter with the neighboring electrons, will have less encounter with the neighboring nuclei. Okay, so more is the electron on the outside, more will be the splitting up of the, so more is the electron on the outside. See the inside electrons in the inner orbitals, they are screened, they are shielded. Okay, So there is less interactions of this electron and more interaction of this electron with the nucleus and with the neighboring electrons. So the splitting up of the energy levels is actually the orbitals, the outer orbitals will split it up more than the inner orbitals. Does not mean that the inner orbital does not get splitted. Of course, their energy level gets splitted, but when the distance between the atoms becomes still smaller, okay, still smaller than the lattice constant. Lattice constant means when atoms come closer together to form a crystal, then there is a minimum distance between the molecules. There is the minimum distance between the molecules forming the crystal. Okay, so that is when when the lattice constant, this minimum distance, and when distance between the molecules is still smaller than the minimum distance, then these orbitals, inner orbitals, also start getting splitting up. Okay, also start getting splitting up, but actually then the structure of the crystal get distorted. Okay, so I'll show you, I'll come one by one to all of this. So it's actually the 3s orbital will have n energy levels. Up to this, I hope it is clear. 3s molecular orbital will split up into n energy levels. Okay. Now, here in a crystal lattice consisting of n atoms, if a crystal I'm taking consisting of n atoms, each atom has its own position. I'm consisting of n atoms. So these are n atoms. Each atom, so these are the nucleus, and these are the electrons in the outermost shell. I'm only drawing the electrons in the outermost shell. These are the electrons in the outermost shell. So what I'm trying to say here is, in a crystal consisting of n atoms, suppose there are n atoms in the crystal, okay, and each atom has its own position. Each atom has its own unique position, because the position of this atom cannot be taken by this atom. Okay, this atom is surrounded by so many atoms, but this atom is surrounded by is not surrounded. Here you see it's had only one atom below and one atom at its side. So whatever this electron will undergo interaction of energy with this atom and this electron and this nucleus, this electron will have different energy, because it will undergo more interactions with the neighboring electrons and with the neighboring nuclei of the atoms. Okay, so each electron will undergo its own way of interaction. Each electron will have its own way, its unique way of interaction with other electrons and with the other nuclei of the other atoms. So no two electrons in any orbital will have the same energy. Like in 3s orbital of this atom, the electron in the 3s orbital of this atom will not have the same energy as the electron of the 3s orbital of this atom, thereby causing splitting up of the 3s orbital into so many energy levels. So 3s orbital gets split up into so many energy levels. So how many energy levels? It gets split up into n levels. It gets split up into n levels. Okay, n energy levels. The 3s orbital gets split up into n energy levels. Now 10 to the power 23 maybe. And this width of this energy level is 1 electron volt. Okay, so how many energy of this what is the gap between two energy levels? Gap between two energy levels will be 10 to the power minus 23. 10 to the power minus 23 electron volt. Okay. This 10 to the power 23 electron volt, this is a 10 to the power 23, sorry, 10 to the power 23 or energy levels. There are 10 to the power 23 energy levels, n energy levels there are, okay, and n energy levels has a width of 1 electron volt. So each, and the difference between two energy levels is 10 to the power minus 23 electron volt. What I'm trying to say here is that this energy levels, the gap between the energy levels is too small for one molecular orbital. It is no longer a molecular orbital now. It's known as energy band. It's an energy continuum. Why it is an energy continuum? Because the electron in this orbital, in this 3s orbital, can jump from one energy level to other energy level easily, because it just requires 10 to the power minus 23 electron volt. So it can jump from one energy level to another energy level and can go anywhere, so long it is in the same energy band, that is 3s band, 3s energy band. It is called 3s energy band. Similarly, the 1s energy band gets splitted up into n energy levels. 2s energy band gets splitted up into n energy levels. Okay, 2p energy band, 2p, what did I say? 2p orbital. 1s orbital gets splitted up into n energy levels. 2s orbital gets splitted up into n energy levels. 2p orbital gets splitted up into n energy levels. They were forming 1s band, 2s band, 2p band. Okay, so this is what is band theory in solids. Okay, now coming to the example of diamond and drawing the energy band diagram. Okay, diamond is carbon atoms packed together. Carbon atoms packed together. Okay, so carbon has an atomic number of 6. So it is 1s2, 2s2, 2p6. Okay, so number of electrons in the outer orbit of each carbon atom what is the outer orbit? This is the outer orbit. Second orbit is the outer orbit. So what is the number of electrons in the, what did I read? What have I written? Oh, 2p2, sorry. So number of electrons in the outer orbit of each carbon atom is 4 electrons to the second orbit. Okay, so number of electrons in the total number of electrons. So 2, you understood, right? 2 in 2s orbital and 2 in 2p orbital. 2s and 2 in 2p. So number of electrons, okay, I'll write it here. So Z equal to 6 for atomic number. So 1s2, 2s2, 2p2. Okay, so number of electrons, total number of electrons in the outer orbit of diamond, that is n carbon atoms, what it will be? Total number of electrons, n carbon atoms. For one carbon atom there are 4 electrons in the outer orbit. So for n carbon atoms there will be 4n electrons. 4n electrons, isn't it? Now total number of energy levels in the 2s orbit of 2s orbit. Total number of energy levels in 2s orbit of 2s orbit equal to how many energy levels? N. 2s orbit, S consists of one shell. Okay, S consists of one shell. So n energy levels. Now total number of energy levels of 2p orbital. 2p consists of 3, right? 3. px, py, pz. Ohm's rule, you just go through. So 3n, okay? 3n. Total number of available states. Total number of available states in 2s orbital. In 2s. How many in 2s? 2s can accommodate 2 electrons, so 2n. Total number of available states in 2p. Now 2p can accommodate how many? How many it can accommodate, not how many is there. There is 2 only, but how many it can accommodate? 1, 2, 3, 4, 5, 6. So 6n is the number of available states in 2n. Okay, so total number of available states is in the outer orbit. In outer orbit is 6n plus 2n, that is 8n. 8n is the total number of available states in the outer orbit of diamond. Okay, n atoms of carbon packed together. Now we are going to draw the energy band diagram. Okay, this is the diagram of energy versus the interatomic distance of carbon, of diamond. So you see here, when the distance between the atoms decreases, okay, the energy level starts getting splitted up, such that some of the energy of the electrons in 2s orbital becomes so high, and some of the energy of the electrons in the 2p orbital becomes so low that they start getting mixing up. Okay, some of the electrons in the 2s orbital, energy of the electrons in the 2s orbital becomes high, and some of the energy of the electrons in the 2p orbital becomes low, that they start getting mixing up. Okay, I have already shown you that 2s orbital has 2n electrons in the outermost. In the 2n orbitals there are 2n electrons, n energy levels, and 2n states, available states. Okay, 2p orbital has 6n states, available states, 3n energy levels, and 2n electrons. I have shown you here. Okay, I have shown you here the calculation. Okay, 2p has 6n available states like px, py, and pz. Each can accommodate 2 electrons. So there are 6n available states, and 2s can accommodate only 2 electrons. So there are 2n available states. Okay, and energy level of 2s gets split up into n energy levels. 2p gets split up into 3n energy levels, px, py, pz. Okay, so total number of available states is 8n, out of which there are 4n electrons, and this electron starts getting mixing up. So when they start getting mixing up, then all the electrons fall into the lower energy band. Okay, the 2s and 2p orbitals start getting mixing up. Okay, so the electrons fall into the lower energy band. Why do they fall into the lower energy band? Because you see here, every physical system, it tries to be in the lower potential energy state. So in the lower energy state, the electrons try to be in the lower energy state. And this is the lattice constant, means the minimum distance between two molecules or two atoms, below which if the atoms become still closer together, then the potential energy increases, or the energy of the electrons increases. Why it increases? Because of electron-electron repulsion. The repulsive force between the electrons becomes higher than the attractive force between the electron and the nucleus. Here the attractive force between the electron and the nucleus is dominant, but here the repulsive force between the electron is dominant, because of which the energy increases after the lattice constant. Okay, So this energy band which is completely filled is called the valence band. And this energy band, it consists of 2n states, that is the 2s orbital, it consists of 2n states, and all the 4n electrons have come to this lower energy band. Okay, this band, 2p band, it consists of 6n states and no electrons. It's called the conduction band. So the valence band is the highest. Valence band means the highest energy band which contains electrons, valence electrons. Okay, the highest energy band occupied by electrons, by valence electrons. And conduction band means the lowest energy band, the lowest unfilled energy band, lowest unfilled energy band is the conduction band. Okay, or which is devoid of electrons is the conduction band. Now in insulator, like in diamond, this is the forbidden energy band, energy gap, forbidden energy gap. No electron can stay here in this state. In this gap, no electron can stay. And this for diamond is 7 electron volt. I guess it is 7 electron volt. Yes, it is for diamond, it is 7 electron volt. Okay, this forbidden energy gap. Now this, like if I draw the 3s, the 2s and 2p, the 2p band is, the 2s band is completely filled, and the 2p band is, there are no electrons and there are 4n electrons. All the 2n electrons and 2n electrons, all these have come and joined the lower energy band. So the 2s band is filled, and this is the valence band, and 2p band is empty, and there is an energy gap of 7 electron volt. Okay, now since this is filled at room temperature, the valence electron cannot cross this 7 electron volt or high energy gap and go to the conduction band. Okay, even if I give an electric field, this valence electrons in this valence band cannot move because there are no unoccupied energy levels. All the energy levels are filled up. Okay, so they cannot even move inside this valence band. Okay, so and it is very difficult to give an electric field of 7 electron volts. So there is no unidirectional flow of electrons. Thus diamond cannot be a conductor. It is an insulator. Okay, so it has to overcome a 7 electron volt of energy gap. So for the electrons to move to the conduction band. Okay, so diamond acts as an insulator. Now if I make the energy band diagram of silicon, let us make the energy band diagram of silicon. For silicon, the atomic number is, for silicon, the atomic number is 14. Z equal to 14. Okay, so it is 1s2, 2s2, 2p6, 3s2, 3p2, I guess. How many? 6, 7, 8, 9, 10, 11, 12, 3p2. Okay, so number of electrons, let us again start. Number of electrons in the outer orbit, outer third orbit of silicon atom, one single silicon atom, is 4, right? So number of electrons in outer orbit of silicon crystal consisting of n atoms, so it will be 4n. Okay, number of energy levels in 3s orbital, 3s orbital gets splitted up of 3s orbital is n. Number of energy levels in 3p orbital will be 3n. 3p gives px, py, pz. Okay. Number of available states in 3s orbital will be 2n. Okay, 2 in each 3s orbital there can be two electrons. So in n 3s orbital, n energy levels, there will be 2n electrons, 2n states, sorry, number of available states in 3p orbital, or why I am writing orbital, energy band it will be actually. In 3p energy band, not orbital, in 3p energy band there will be 6. So 6n. In one 3p orbital there can be 6 available states. There are 2 electrons, but there can be 6 available states. So a number of available states in 3p energy band will be 6n. In one atom there can be 6 available states. So in n atoms there will be 6n available states. Okay. Now let us draw the diagram. We have 6n states in 3p energy band, 2n states in 3s energy band, 3n energy levels in 3p band, n energy levels in 3s band, and 4n electrons is the total number of electrons in the third orbit of silicon crystal. So let us draw the diagram. Okay, this is the diagram for silicon crystal, the energy versus the interatomic distance, and as the interatomic distance decreases there is overlapping of the atomic orbitals. You can see, so 3s atomic orbital, which consists of 2n electrons. When it forms a crystal, it consists of 2n electrons, n energy levels, and 2n allotted states, available states. Similarly, the 3p atomic or molecular orbital, whatever you say, the 6n states, when it forms a crystal, it has 6n states, n levels, and 2n electrons. N energy levels, 6n available states, n energy levels, and 2n electrons. Now there is when the atomic orbital starts getting mixing up, then some of the electrons in the 3s orbital gain energy and move up. Some of the electrons in the 3p orbital loses energy and moves down. Okay, so there is intermixing of the electrons, energies of the electrons. So there is a state where it has 8n states and 4n electrons, 8n states and 4n electrons, and then the electrons move to the lower energy band. Lower energy band, that is 3s band, it moves to, and it has 2n, 3s band has 2n states and 4n electrons. All the 4n electrons, this 2n electrons in the 3p band and 2n electrons in the 3s band all move to the lower energy band. And this lower energy is no longer a 3s band. Okay, there is a mixing of 3s and 3p band, you can see. So it is no longer a 3s band. This is the lower energy band and this is the higher energy band. The higher energy band has 6n states and no electrons. The lower energy band has 2n states and 4n electrons. All the 4n electrons, 2n electrons in the 3p band and 2n electrons in the 3s band has moved to the lower energy state. Okay, and there is a forbidden energy gap of 1.1 electron volt. So at 0 Kelvin, this is a semiconductor, silicon crystal. A semiconductor behaves like an insulator where all the electrons are there in the valence band. This is the highest occupied band and is called the valence band. This is the lowest unoccupied band and is called the conduction band. Okay, so this is the conduction band and this is the valence band. This I have shown at room temperature. Of course, you can see electrons in the conduction band as well. but at 0K there are no electrons in the conduction band and all the electrons are there in the valence band. Okay, now at room temperature, some of the electrons from the valence band, that is from the 3s, will move to 3p. Okay, so there are some unoccupied levels in the valence band and there are some occupied levels in the conduction band. Thereby, the electrons will start conducting if an electric field is applied. At room temperature, some of the electrons from the valence band will overcome this forbidden energy gap and will move to the conduction band. So there is some occupied energy levels in the conduction band, and these electrons in the conduction band, when an electric field is applied, they will start conducting. Okay, so silicon will start conducting. Okay, so that is the difference between an insulator and a semiconductor, but at 0 Kelvin they are both same. Their valence band is completely filled and the conduction band is completely empty. Okay, so this is how the different solids behave differently. The free electrons in some are free to move, in some occupied. When the valence band is completely filled, the free electrons are not free to move, and even in the valence band, that happens in an insulator. Okay, but in metals, in sodium, the free electrons, the valence band, are half filled. Okay, so conduction band and valence band overlap each other. So free electrons are free to move in the valence band, which is same as the conduction band. Okay, because in sodium they overlap each other, so they are always ready to conduct. Okay, so that is all for energy band in solids, and in the next lecture we will be doing electrons and holes in semiconductors. Thank you.